When we look at the outer solar system, at the delicate, icy rings circling Saturn, we tend to view space exploration as an exercise in pure scientific curiosity. But that peaceful perception is a relatively new luxury. If we trace this technology back to its origin, we fall directly into the smoke and rubble of 1940s Europe. The first human-made vehicle to touch the edge of space was the German V-2 rocket. It was a vengeance weapon, designed by the military to rain tons of high explosives down on London and Antwerp. Space exploration sits on a foundation of ballistic destruction. The rocket's initial design goal was to level city blocks. As Germany collapsed at the end of World War II, American and Soviet forces scrambled to capture these rockets, along with their chief architects like Wernher von Braun. They were moved to testing grounds in the United States and the USSR. The onset of the Cold War changed the rocket's trajectory. The military now required much larger vehicles capable of delivering heavy nuclear warheads across oceans. Comparing the WW-2 rocket with nuclear-age requirements, the ICBM had to be exponentially larger, using vastly more powerful propellants. The sheer thrust required to throw a multi-ton nuclear core globally accidentally gave these rockets enough velocity to break the atmosphere and stay in orbit. The space race functioned as a geopolitical show of force. Launching Sputnik was proof that a nation could drop an atomic warhead on any city on the planet. Because of political urgency, neither nation had the time to build dedicated spacecraft. Instead, they took the nuclear delivery systems they already had and modified them for human flight. Early astronauts were bolted directly on top of volatile hardware like the Redstone rocket. They were essentially riding weapons. These first flights were brief suborbital hops. They served to prove that humans could survive the crushing weight of launch acceleration and be safely extracted from the ocean. Reaching actual orbit required longer engine burns and much higher speeds, which highlighted massive reliability issues. Boosters frequently exploded on the launch pad, proving that mass-produced military hardware was far too erratic for human cargo. Brute force is enough to lob a warhead on a parabolic arc, but it cannot keep a fragile human crew alive in the vacuum of space. The technology needed precision engineering to survive. To master the precision required for a moon landing, NASA initiated Project Gemini. This was an iterative testing ground to figure out how to actually pilot a spacecraft in orbit. Stepping outside the capsule revealed that the stiff, pressurized fabric of a spacesuit ballooned in the vacuum. Simply bending a joint became a physical struggle that left astronauts exhausted in minutes. The orbital physics of these missions proved to be completely unforgiving. During Gemini 8, a single stuck thruster fired continuously, sending the spacecraft into an uncontrolled spin that nearly cost the crew to black out. These near disasters forced a massive shift in engineering. NASA moved away from crude military switches, instead integrating solid-state computers and highly redundant life support systems that could catch their own errors. The political pressure to beat the Soviets forced engineers to solve orbital mechanics problems in just 5 years. They had refined the crude ICBM into a controllable, sophisticated spacecraft. Once the political victory of the moon landings was secured, funding for human exploration collapsed. But the technology forged in the Cold War was about to be used for uncrewed, purely scientific missions. This map shows a rare orbital alignment. Jupiter, Saturn, Uranus, and Neptune were moving into a formation on one side of the Sun that occurs only once every 175 years. This opened a window for a single spacecraft to visit all of them. To cross these immense distances, a probe would use a gravitational assist. By flying precisely behind a planet, it could steal a tiny fraction of orbital momentum, slingshotting forward and gaining the speed necessary to reach the next target. Surviving this journey meant enduring the freezing vacuum far beyond the reach of solar power. The Voyager probes relied entirely on the heat of radioactive decay to stay operational. Because radio signals took hours to travel back and forth to Earth, the spacecraft had to be its own pilot. It relied on autonomous fault protection systems, applying the lessons of Gemini's hardware failures to keep itself running in deep space. When Voyager reached Jupiter, it transmitted data showing a turbulent atmosphere of complex eddies and volcano moons, a far more active environment than ground-based telescopes ever suggested. Decades later, the Cassini mission carried even more advanced technology to Saturn. It was equipped with radar mapping tools and atmospheric probes capable of peering right through thick, opaque environments. This radar image shows massive bodies of liquid methane resting on the surface of Titan. On Enceladus, Cassini detected saltwater plumes erupting from the icy crust, revealing a warm subsurface ocean similar to the environments that support life on Earth. We took the rocket, a blunt instrument of war, and spent decades refining it into our primary instrument for understanding the universe.